So now we're going to focus on the problem of multiplying two n-bit numbers. It seems like a very easy problem, right? You learned this in grade school. It turns out that the grade school strategy, as you're going to learn, requires O of n squared computation. We're going to try a divide and conquer strategy. That'll get us another O of n squared algorithm, but if you're a little bit smarter and a little trickier, you can actually get something that's even faster, that's closer to n to the 1.5. Let's talk about that. Now we're going to consider how to multiply two n-bit integers. As a warm-up, let's first consider how to add two n-bit integers. Let's take two 6-bit integers, x, which is 53, which is 110101 in binary, and y, which is 35, which is 100011 in binary. Now we're going to add them together. Let's think about how you add two numbers together like you did in grade school. You first go to the first column, you add those together. If that exceeds the base, which is in this case 2, you carry the 1, and then you put that in, add that to the next column. You add those three numbers together. Again, you have to carry the 1, and you go to the third column, and so on and so forth. Now let's consider the running time of this algorithm. You'll notice that we had to look at most n plus 1 columns. In this process, we created n plus 1 columns. And for each of those columns, we had to do a number of operations. But the total of operations was just simply adding 3 bits. So in total, we had to work on O of n columns. And in each column, we had to do O of 1 many computations. 3 is O of 1. So in total, the total running time of adding two n-bit integers is O of n. Okay, now let's get back to multiplying two n-bit integers. Let's let x and y be 13 and 11 respectively, here written in binary. Perhaps the most naive way to multiply x times y is simply to add x up y many times. Let's think about the running time of this naive algorithm. The first thing you have to do is add x to itself once, and that takes O of n times. But of course, we're going to repeat that operation y many times. And how big is y? Well, y can be as large as 2 to the n. The total is then going to be roughly n times 2 to the n, on the order of n times 2 to the n, which of course is exponential in n and not particularly desirable. A much better method is the quote-unquote grade school algorithm, the one you learned when you probably were in 1st or 2nd grade. Recall that the grade school algorithm involves taking digit by digit of the bottom number and multiplying it by the top number and then shifting that over a column as you move over digits. In the end, you have to add up all of those terms together to get the final total. Let's think about the running time of the grade school algorithm. Note that the grade school algorithm has 2 phases. You have phase A, which does all the digit multiplication, and then there's phase B, which is the full summation of all those numbers you computed in phase A. In phase A, we had to do n rows of computation, and every one of those rows required us filling in at most 2n columns of operation, and filling in an entry required O of 1 many bit operations. So the total computation required to do phase A is on the order of n squared. Phase B required us to add up all of those n numbers. Each of those numbers had 2n digits, so again, phase B also required O of n squared computation. So now we have an algorithm that can multiply two n-bit numbers in time O of n squared. The only remaining question now is, can we do better than this? It turns out, yes, we can. We're going to borrow an idea from Gauss, who came up with this when thinking about complex numbers. So let's consider how we might be able to design a faster algorithm for multiplying n-bit numbers. Let's recall that the letter I means the square root of -1, so that I squared is equal to -1. The thing we want to answer is, how do we multiply the number a plus bi times c plus di efficiently? Notice that we can achieve this by doing 4 multiplications and 2 additions. Of Gauss, of course, was that he figured out that we can actually do this with only 3 multiplications. How is that? You need to make one simple observation, and that's that the quantity BC plus AD can be written as the combination of three multiplications, a plus b times c plus d minus ac minus bd. This might seem like more work, but remember that we already completed the multiplications a times c and b times d, so we can reuse these. Okay, now we're going to use this trick to make a divide and conquer algorithm for multiplying n-bit integers more quickly. For simplicity, we're going to assume that the two numbers we're given, they have n bits, and n is a power of 2. We can always ensure this by padding the beginning of these numbers with additional zeros. So the way that we create a divide and conquer strategy is by taking these n-bit numbers x and y, and we break them each into two halves. The first n over 2 bits of x, and then the next n over 2 bits of x, followed by the first n over 2 bits of y, and then the next n over 2 bits of y. Mathematically, x is still just 2 to the n over 2 times xl plus xr, and y is 2 to the n over 2 yl plus yr. And we can now compute x times y as follows. Using the distributive law, we can see that x times y equals 2 to the n times xl times yi plus 2 to the n over 2 times xlyr plus xryl plus xryr. Okay, this is now going to give us our first draft of a divide and conquer algorithm. So now let's define a method in Python called mult of x comma y. I'm not going to be totally using Python code here, so this is like a pseudocode, but let's imagine that you're given x times y as lists of two n-bit numbers, so it's just a list of the digits of these two numbers. We can compute the lengths of these numbers n, and of course in the base case, if each of these two lists has only one element, then we simply just return the product of these two elements. Our next step is to break x and y into xl and xr and yl and yr. Next, we recursively perform all 4 pairwise multiplications. Now, using the formula that we worked out above, we can combine a, b, c, and d to get the result we want. I know, technically speaking, I'm not following the type system that I suggested above, where the numbers are lists of digits, but let me cheat on this one and use some of my own pseudocode. The first few steps of this algorithm take no more than O of n time. However, then we make 4 recursive calls to mult. So we need to account for this by adding in 4 times t of n over 2, since all of these multiplications are of numbers of length n over 2. Finally, we have an O of n operation, since we have to add 4 n-bit numbers together. The total running time is then t of n equals 4 times t of n over 2 plus O of n. As we're going to see, this means that t of n is actually on the order of n squared. We'll show you why that's true soon. It's important for you all to know that the word of the day is albatross. That's albatross. Okay, so that technically wasn't a faster algorithm. We haven't actually used Gauss's trick yet. So how do we do that? Let's remember what Gauss said. He observed that you can multiply 2 complex numbers and write it in terms of this, which only requires 3 multiplications. It turns out that the same is true for the combination xryl plus xlyr. The same distributive law trick can be applied here. And it turns out this is going to give us a faster multiplication algorithm. Let's call this fastmult. Fastmult is very similar to the mult algorithm we used before, but it has some additional tricks. Notice that fastmult only does 3 multiplications, and when it returns is an interesting combination of those 3 multiplications, which is precisely the same trick used for reducing the number of multiplications when you're multiplying 2 complex numbers. Reducing the number of multiplications is significant, and it's going to give us a faster running time. Let's analyze the running time now. The first several steps, as we said, take no more than O of n time. The next 3 steps of the algorithm require 3 recursive calls to fast mult, but each of those are on numbers that are of size n over 2 bits. That reduction in the number of recursive calls to fast mult is very important, as we'll see. Since the last step takes only O of n time, the total running time for this algorithm can be written as T of n equals 3 times T of n over 2 plus O of n. We haven't quite taught you how to simplify these recursive expressions for running time, and we'll get there. But for now, just know that this is going to simplify to T of n equals n to the log base 2 of 3, which is roughly n to the 1.59. As you'll notice, we now have an algorithm that's faster than O of n squared. It's now just over O of n to the 1.5, which is great. We're now improving the running time of this algorithm significantly using a smarter divide and conquer strategy.